بسم الله الرحمن الرحيم. السلام عليكم. 10th grade at Rital International Academy. Good day to you. I hope you will remain safe and you will remain at home. This lesson is for you. We will continue our journey in physics by this video. The outcomes I expected from each of you would be you will be able to describe how light waves interfere with each other. And the second outcomes I expected you will identify the conditions required for interference to occur. The third outcomes I expected from you define the constructive and destructive interference. And the last but not least define coherent and incoherent light. So let us start our journey combining light waves. We will study the case with two light sources interact with each other. As you know, we have combining light waves. To understand how light waves combine with each other, let us review how other kinds of waves combined. You have to use your imagination in this case. What if we have two light waves interact with each other? What if you have this wave interact with that wave at this point? What do you expect is going to happen? Okay, pause the video and try to figure out how they will interact. By yourself, imagine and use it in this lesson. So if two waves with identical wavelength interact, they combine to form a resultant wave. So I have this simulation, you know me, I love simulation. I have this wave, this light wave with yellow light. What I expect, if I add another yellow wave in here at the bottom, what is going to happen here as a resultant wave? So I hope you will be aware with me in this demonstration. So I add another wave. This wavelength, this wavelength should be identical. So there are two wavelengths. What is happening here? So be aware in this case. I paused them. Look, I paused at the middle here. I have minus 45 centimeter at the bottom here, and I have minus 45 centimeter at the bottom here. What do you expect the resultant we calculated in the other side? After that, I will expand the screen. You will see the result. But I want you to understand it and to expect the behavior of the light when they interfere in each other. Here with the I component, they are interfere at this point. They are interact at this point. What is going to happen? You could see that. Recognize that at the bottom here, minus 45 centimeter. It is not a condition to be minus 45 centimeter. It might be positive 49 centimeter, positive 49 centimeter in each case. So they are very identical at the wavelength and at the phase. We call this at phase because they have the same wavelength, they have the same direction, overlapping between top and top. We have, and previously we have overlapping between bottom and bottom. We said that they are on phase in each other. So what do you expect we will have as a resultant waves? Let us see. Calculate by yourself and see that by me now. Okay, we have the resultant waves. We have top and top, 49 in each. We add them together, we end up with 98 centimeters. So when they are at the same phase with same color, which means same wavelength, we end up with an expanding resultant waves with higher amplitude equal 98 centimeter. Okay. So could see that again. 44, 44, and up with 88. Minus 47, minus 47, minus 94 centimeters. So we call this, because they are same light, same direction, they overlap totally with each other. No difference in between, they are zero. Yeah, the difference equals zero. We call this an constructive interference. Now I have another example here. Look at this case. They are interact, but there's something different between this case and the previous example. I hope you'll be able to figure out that by yourself. So let me pause. Might help you. Okay. At the top I have negative 11 centimeter. At the bottom I have positive 11 centimeter. What do you expect the resultant waves would be? Look at this. I move it here. So we add them together. So we have minus 11 plus positive 11. We add them always. We gain a 0. So we call this a destructive interference. Why we call it destructive? Because they are interact destructive way, different from the previous example. As we see, we have here, we have bottom at top equally, with inverse sign. They are equal at absolute value, but with inverse sign in each case. Negative 24, positive 24. When we add them together, we end up with 0, which means constructive. There's no resultant waves at all. Here it's equal 0. So the two light sources disappear in this case. This is something miraculous. And in spite of the fact we have a light source, but they are interact to each other, we end up with no light. So we call this by destructive interference in this case. The difference between this example and the previous example, we have top at bottom and bottom at top. Previous example was top and top, bottom and bottom. We call it constructive interference. Now it's destructive interference. You can see that here. Look, phase shift. Look at this. Phase equal here 0. And for the other one, phase shift equal 180. So there are a difference between both by 180 degree from here to here, 180 degree. So the phase difference 180 degree, we have a destructive interference. This resultant wave has the same wavelength as the component waves, but according to the superposition principle, because they are overlapping each other, its displacement at any instant equals the sum of the displacement of the component waves. The result waves is the consequence of the interference between the two waves. So I have this A and B in each. Look, I have first wave here. This is the first wave. Interact with the second wave. They are overlap top and top and bottom at bottom. So we add them together. We end up with wave with violet light, violet color, as you see. So we add them. In a B, we have a different case. We have a top of the wave overlap with a bottom of the wave, or crest of the wave overlap with a trough of the wave. They are when we add them together, we end up with these waves, the resultant waves. You could recognize that the waves with higher crest is greater than the waves at the bottom, so the waves would be at the bottom. And as well here, as well here. A light source that has a single wavelength is called monochromatic, and we always prefer to use a laser source as a monochromatic light. So this is the demonstrations we could see here. Waves must have a constant phase difference. This is the conditions for the interference to be occurred, for interference to be observed. If two waves to produce a stable interference pattern, the phase of individual waves must remain unchanged relative to one another. So the phase must be unchanged. If the crest of one wave overlaps the crest of another wave, figure A here, over a crest and crest, and trough and trough, crest and crest. The two have the phase difference of 0 degree, and we said they are in phase. We saw that at the simulation program previously. Okay, in case B, give me the definition by yourself. Give it to me and pause the video, and after that try to compare my answer to your answer. If the crest of the one wave overlap the trough of the another wave, crest overlap with trough, trough overlap with crest, the two waves have the phase difference of 180 degrees. We saw that at the simulation applet previously, and we said that they are out of phase. So if they are in phase, that means top with top, crest with crest, trough with trough. If they are out of phase, we said that top with trough, trough with top, and so far, so forth. Waves are said to have coherence when the phase of difference between two waves is constant. So it must be constant, and the waves do not shift relative to each other as time passes. Sources of such waves are said to be coherent. So why we call them coherent? Because the phase difference between two waves is constant, does not change. Like this case, 0 and 180 degree. In all times, if we keep tracking the waves, it would be 180 degree. Here, it would be phase difference 0 in all times. As the waves passes through, it will be 0. So we said that they are coherent. Here, suppose we have this two identical light sources. When two light bulbs are placed side by side, no interference is observed, even if the lights are the same color. Why? Try to explain that by yourself. The reason is that the light waves from one bulb are emitted independently of the waves from the other bulb, because they are independent, because they both contact with different energy sources, so they are independently. Random changes occurring in the light from one bulb do not necessarily occur in the light from the other bulb. Suppose in this one, it is this way, and this one in this way. So between the light waves from the two bulbs is not constant. The light waves still interfere. They are interfere, but the condition for the interference changes with each phase change. And therefore no single interference pattern is observed. Light sources of this type are said to be incoherent. So here we have two identical lights, but they are incoherent. They are random because they have different energy sources, and so the resultant here, look here, minus 18, here minus 34. If you add them, you end up with minus 51. But we could not call this an interference pattern. So if I have, it's not conditioned to be a constant. So here we have this yellow color with red color. They are interfering in this case. And we could see minus 4 with minus 49, minus 53 with different color, as you see. So the conditions for interference is same light color, same wavelength, and they should be in phase in each other. Thank you for listening to me. Good day for you each.